Well, some of y'all pointed out to me. This is the second time you fixed my Blackboard errors this semester. I didn't have the access to the folder set right that has the tapes in them, so I fixed that. Grab your name pen over. So I fixed that. So you should have access now to this to all the folders in Blackboard, but this one with the notes and the video, right? So the video is working. That's a YouTube video, so I did test that. So that was working, okay, and then the class notes were there, okay. So so you can find the stuff from last time if you were looking for it, right? So I was going to point that out anyway, right? That there's where the video lecture will be. So as usual, here's what I usually display at the beginning of class, and this is just the homework list from WebAssign. So I didn't check right before I came over here how many people had enrolled, but quite a few people had already enrolled. So if you're not enrolled, go ahead and enroll, right? You don't have to actually pay. When you pay, that's called registering, which is different from enrolling in the class, but you can still enroll in the class and work on your homework, right? Through Labor Day, which is still a couple of weeks off, right? So so I've got that first homework posted, and you know, through last time you could probably have worked on the first few problems from that, but not that whole homework. But we'll finish the notes for that first homework today, and so you should be able to finish that first homework, okay? And so that's due on August 31st, right? Which is a week from today. So it's not that long of a homework. Let me open this though. Just let's just look at it here briefly. So let me click on it. So most of it is, I think, pretty easy to understand. I mean, the questions once you've sat through the lectures, right? So for instance, on this very first one, they show you a vector here with the initial and the terminal points, right? Okay. And then they just want the component form of the vector, right? So that's that is the coordinates for the vector if the initial point was at the origin. So we often think of vectors with their initial point being at the origin at 0, 0, right? Rather than this vector, which is just in a general position there in the first quadrant. And so the way you find component form, right, is you simply take the difference in the x coordinates. So take the terminal point x coordinate, right, and subtract off the initial point x coordinate, and same thing for the y coordinates, right? Take the terminal point y coordinate and subtract off the initial point y coordinate, and that would give you just what's called the component form, and that's just a shorter version of a representation of the vector, right? Other than, well, you could draw a picture of the vector, right? Or writing down both the initial and the terminal points, right? In component form, you just really are writing down the terminal point because you're always assuming that the initial point is at the origin. Of course, the coordinates are 0, 0. Now, to type that in though, right? Since we use some special notation for vector coordinates, we use the pointy brackets there, right? Instead of parentheses or braces. You need to find that so you can type that in, right? And I think you do that using the math palette, right? So come over here on once you've positioned your cursor here inside the answer box, then you'll get this math palette on the right hand side. And so choose vectors there, I think, and it will give you, I think, that those pointy brackets, right? So let's see if that works. So yeah, there we go, right? Okay, so so we can put in there what the answer is. What is that there? 5 minus 1 is 4, right? And then I guess I need the comma. Oh, I didn't even type that in right though. So 4, and then what? 4 minus 2 is 2, right? Okay. And so there's the component form of that vector. Let's see, what else are they asking us here? So now, of course, in WebAssign, right, it's difficult to graph. And so they'll often just give you multiple choice questions for graphs. That's why here in class, I'm going to try to have you do, some activities in class where you're actually graphing by hand, right? Because that's going to be important if we have to draw vectors on a test, because our tests are going to be on pencil and paper, right? And so, so that's why we do a lot of things here in class by hand. But let's see, can we pick this out? Oh, they just want the vector, right? So what was it? 4, 2, right? So that has to be this one, correct? And so see how easy that first problem is. And then we can submit our answer, and I hope I got it right, so I can get at least a few points here on the first homework. Did I get it right? Yeah, I did. See, so you know, you don't have to submit your homeworks all at the end. You can submit problem by problem. And I think I've got it set. Oh, I better check this because I haven't checked this for this class in a while. But I think I've got it checked for 5 submissions per problem. So you get 5 chances of getting it right. Okay. But now, unfortunately, the system is not that friendly. So when you run out of your 5 chances, you run out of your 5 chances. And there's no way in this system to ask for a similar problem. You've just sort of blown that problem. Okay. So look, so here's the thing. When you start running out of submissions, ask someone. So you can email me, right? Isn't there ask your instructor there button? Is that, yeah, there it is, ask your teacher. So if you click on ask your teacher, it will send me a copy of the problem and also the answer that you had typed in that apparently was wrong, right? Because otherwise you wouldn't be asking me. So so I can respond to you, and I'm pretty good about responding to those. However, sometimes often you guys will be working on your homework really late at night because the due times are often at midnight. So if you're going to be asking me like at 11 p.m., probably I'm not going to see that until the next day. But anyway, I do respond to those. And remember, I'm going to be in the Math Center, North 925 in the one main building from 2 to 5 on Mondays and Wednesdays. So right after class here or shortly after class, I will be in the Math Center. So you can find me there also and ask questions. Okay, as well. I don't think there was any notation otherwise in this homework that was particularly challenging. If you have to enter square roots, I think you can also do that from the math palette. Let me click on here and see if we can see the math palette. Oh yeah, see there's the square root right there. And sometimes you have to enter square roots if the question wants your answer in exact form. So for instance, if a magnitude of a vector is square root of 47, and it doesn't say give a decimal approximation, then that means it wants square root of 47 exactly, right? So you might have to type in, with the radical sign, square root of 47. So keep that in mind. That's one thing that drives students crazy about WebAssign is read the instructions carefully, because if it does not say in a problem give a decimal approximation, it probably wants the exact answer. Decimal is not exact, right? That's an approximation. So be careful about that, okay? Decimal approximation versus exact form. And, sometimes exact form can be clumsy, right? It might be a complicated expression, but you just have to build up the expression using the math palette and try entering it that way, okay? All right, so anyway, have y'all started on this? Anybody started on this so far? I know several people are enrolled. No? Okay, all right. Well, okay. That's fine, but don't wait until don't wait until Wednesday when it's due next Wednesday at 11 p.m. to start on it. That's going to be too late, right? Okay. So you're all successful math students, so you know not to do that. But just to remind you, the WebAssign has lots of help, and I encourage you to use the help features. So one thing it has is it will let you practice another version, but it won't give you credit for that practice version, right? So it will let you practice another version, and sometimes it has. Does it have in here anywhere? Like not similar problem, but it's like example, or maybe master it would be it. where it sort of, gives you instructions or shows you how to do a similar version of the problem. Oh, here it is. Here's a video, right? Watch it. So it'll show you a video of how to do a similar version of that problem. And all of those help features are great. So, you should use them, of course, right? Because you paid for them. But remember, the tests, of course, don't have help features, right? So try your best to work the problem without using the help features first, right? Just using your notes or what you recall from class. But then if you're just completely stumped, of course, then use the help features, right? But I don't want you to become over. My point is, I don't want you to become over reliant on the help features, okay? Because then that's not available on the test, and then, then you come in to take the test and you start getting nervous, and that screws everything up. So that's my warning about the help features, except for ask your teacher. So that one you can use sort of freely, right? Okay. But you don't get instant response on that one always. Okay. All right. So much for looking at WebAssign for the time being. All right. Well, let me see if I can find the right notes. Yeah, this is them. So here's where we were last time, and we're going to continue with that. But let's practice a little bit what we learned last time, or I hope what you kind of learned last time, right? Okay. So we have a little recall practice here. So if you've got your graph paper that I gave you last time, you can use that, but you can use any other paper too that you want to. Anybody want a piece of paper? Free? Okay. No? Yeah, they're all. Okay. All right. Here's what I want you to do. So there's a vector. I don't have a picture of it, but obviously that's a vector because you see the pointy brackets, right? And you have the initial point and the terminal point. So that's kind of the clumsy way of writing down the vector, right? With the initial point and the terminal point. But I want you to take that and put it in component form, right? The sort of simplified version of the vector, just what we did in that first problem on the WebAssign a moment ago, right? Okay. So put it in a component form. You don't have to draw a picture of it. And then once you've got it, you can do it in this form as well, but it's easier once you've got it in component form, find the magnitude. All right, find the magnitude of that vector. Right? Remember, that's kind of the length of the vector. In geometric terms, that's kind of the length of the vector. But we use magnitude for other purposes with vectors, not always geometric. So y'all remember how to do that. I'm going to come around if you need some assistance, just ask me. We're going to do something. Okay. That's fine. Or you can look your notes, or you can ask your neighbor, right? So then you can ask them, I do. Oh, yeah. Okay, so it looks like you all remember everything. Darn it, I was hoping to. So looks like I won't be able to. Let me lower this and then we'll do the calculations here, which I already got these right. So in component form, right? It's just what we mentioned for that web sign problem, right? Just take the difference in the coordinates, right, between the initial point and the terminal point, right? So take 3 minus a minus 2, right, for the first component, and then 1 minus a minus 5, if I can squeeze that in there for the second component, right? So you get what, 5 and 6. So that vector, if we sketch that right, you're not asked to make a sketch, right? But if you did sketch it, it's going to come right up here in the first quadrant somewhere, right? Okay. Almost, that would almost be at a 45-degree angle, right? It would be at a 45-degree angle if these two coordinates were the same, correct? Okay, so if this were 5, 5, or 6, 6, that would be exactly a 45-degree angle, right? From the x-axis for that vector, but not quite. Okay, so maybe a little bit more than 45 degrees there. So this terminal point in component form is 5, 6, right? And now the magnitude, right? Which is you can think of that geometrically as the length of this line segment, right? Well, of course, you just derive that from the distance formula, right? So you have the square root of 5 squared plus 6 squared, right? So that's what, 25 plus 36, which is 61, right? So there's our magnitude, is the square root of 61. Did I get that right? Okay, great. Well, then, you really kind of got the first lesson there, right? Of last time for vectors. And then when we were finishing last time, we were kind of extending our knowledge of kind of that very basic knowledge of vectors, right? So we were talking about how to do operations with vectors, because vectors are mathematical objects, right? So we want to be able to do operations with them similar to real numbers, which in the context of vectors, right? Remember, we call scalar numbers. So so we have vectors and scalars, right? And scalars are just what you would just think of as a real number from a previous course. So the first thing that we learned last time, right, is how to add two vectors together. And we drew a picture of that, how that looks geometrically, right? When you're adding two vectors together in visual form. If you're adding the vector u and v together, right, you simply draw the vector u and then attach v to the end of u, right? So you take as the initial point of v the terminal point of u, right, and then draw out the vector v, and then connect the initial and terminal points, right, in this diagram, and that gives you a picture of the sum of the two vectors. So u plus v in this picture would be this sort of diagonal vector here, right? In the picture. That's how it looks geometrically, but algebraically or arithmetically, it's even a little bit easier. So if you're adding two vectors and the vectors are in component form, so if you're adding vectors and the vectors are written in component form, it's so easy to find the sum vector. All you have to do is add the components of the two vectors, right? So add the first component of the two vectors and add the second component of the two vectors, and that gives you the sum of the two vectors in component form. Remember that sum in this context of adding vectors, we're often going to call that the resultant. Okay, so when you hear me use the term resultant, that means sum or possibly difference of two vectors, but we'll talk about taking the difference of two vectors here in just a second, right? Another operation we perform with vectors is what's called scalar multiplication. So if we want to take a number and multiply it times a vector, how do we do that, right? So we're mixing up objects, right? We're taking a real number and multiplying it times a vector, which is not quite the same as a real number, right? Okay. But that a scalar multiplication is very easy, okay? So when you take a scalar, so in this expression, C here represents just a number, and you multiply it times the vector, the way you do that is just take your scalar and you multiply it times both of the components, right? Okay. So scalar multiplication is very easy. Just take the scalar, multiply it times both of the components. Now, we're going to be doing other types of operations with vectors, okay, that also kind of look like multiplication, right? But they're not good, but they're going to be slightly different. Scalar multiplication is one operation, one multiplication operation that we perform with vectors, but that's not the only one. Because you may also ask yourself, okay, here I'm taking a number and multiplying it times a vector, but what if I want to take a vector and multiply it times a vector? What would that mean? Okay, right? So, see, that's a little bit different operation. Well, we're not gonna get to that quite yet. Okay, so we're just going to start with this very simple scalar multiplication. Now, once you've defined scalar multiplication, then that gives you a method of talking about the negative of a vector, right? So what do we mean when we put a minus sign in front of a vector? Well, we can interpret that as the scalar minus 1, because that's a real number, right, times the vector. So minus v, we can think of that as being the scalar minus 1 times v. But now that we've defined scalar multiplication, we know what this means, right? You just take the minus 1 and multiply it times each of the components. So you just get the negative of each of the components. So when you take the negative of a vector, it just gives you the negative of each of the components of the vector. That seems very simple and makes perfectly good intuitive sense, right? Okay. Let's just show a little bit a little diagram of scalar multiplication here and what effect that has. So here's a vector W. I don't know what the initial and terminal points are, right? Okay, or I don't know what the component form is for the vector W. But when you multiply the vector W times a scalar, the geometric effect that's going to have is it's going to lengthen or shorten the vector, okay? So if you were to take the vector W and multiply it by 2, you're in effect going to double the length of the vector, right? Or if you multiply W by 1/2, you're going to cut the length of the vector down by 50%, right? You're going to half the length of the vector. And if you take W and you take the negative of W, in other words, you multiply it by the scalar minus 1, what you're going to do is reverse the direction of the vector. Okay, so you're just going to flip the vector in completely opposite direction. So if this is the direction of W, right, then the direction of minus W would just be 180 degrees from that. Okay. Here's a picture of minus 3/2 times W. So what does that do? Well, it changes the direction of W, right? Because this is a negative scalar. and then it's going to extend the length of W by 3/2, right? So you're going to get a little bit bigger vector here. So that's how scalar multiplication works geometrically, but algebraically, it's very simple, right? When you do scalar multiplication, you're just taking the scalar, whether it's positive or negative, doesn't matter, and you're multiplying it times each of the components of the vector, right? If the vector is written in component form. Now that we have negative of a vector, now we can define subtraction for vectors, right? So we start off by doing addition for vectors, right? And now that we know how to find the negative of a vector, the minus of a vector, then we can define now subtraction. How would that work? So if you wanted to take u minus v, right? So if you wanted to subtract these two vectors, well, that would be the same as taking u plus the negative of v, right? Okay. So u minus v would be, logically, that would be the same as u plus the negative of v. But we know what the negative of v is, right? We just talked about that, right? You just change the sign of both of the components. So u plus minus v is just going to be sort of what we would expect, right? It's going to be, instead of adding the two components together, we'll subtract the two components, right? So u minus v would be the difference in the first components, and then also the difference in the second components, exactly what we would expect. Let's draw a picture of that, though, because the picture is kind of informative. I like to draw pictures of vector operations when I can. Actually, we're going to be doing pictures of vector operations a lot because it's really useful. So what would, so let's think about, what would u minus v look like? So here's the vector u that I started with, and here's the vector v. So over here on this side, I have, this is a diagram of adding u and v, right? But now let's see what a diagram of subtracting u and v look like. So remember, you're thinking of u minus v as being the same as u plus the negative of v, right? And so we are indeed, when we subtract two vectors, we are adding two vectors together, except we're adding the negative of the second vector, right? Now, what does the negative of v look like? So in this picture, what would the negative of v look like? When you take the negative, what does it do? I said it just what? Just changes the direction 180 degrees, okay? So if this is v, right, then minus v is going to come in this direction, right? In that direction. In fact, where's it going to go? Let's see. What are the components of v? Looks like the first component is 4, right? And the second component is 2. Well, then that means in the negative of v, the first component would be minus 4, and the second component would be minus 2. So minus v is going to come out just like this, right? So there's the vector minus v. So I want to take that vector and add it onto u, right? Because u minus v is u plus the negative of v. Now, remember in the picture I said, how do you add vectors together geometrically? Well, let's see. So you start off following u, right? Okay, so there's the vector u. And then what do you attach to the end here? Negative v. Here's what negative v looks like. So when we attach negative v here to u, we're going to get a vector that comes down like this, right? From the endpoint of u, right? Because this is the direction of minus v, right? Minus v goes in this direction. Now, how far is it going to go? Let's see. Y'all help me here. It's going to go what? How far? This direction? To the left. How far? What? 4. And how far does it go? Down 2. So let's count that off. We're going to go down 2, right? But starting from the end of u, correct? So we're going to go down 2 and over what? How much? 4? Oh, so my picture here, I didn't draw my arrow very good, did I? Let's erase it a little bit. Let's try that over again. So starting from the end of u, right? I'm going to go like this, because that's what the vector minus v is, right? See, here's the vector minus v. Now, how do you get the sum finally? Just start at the beginning of u and go to that endpoint where you ended up, right? So there is the vector. Here is the picture of the vector. Here is the picture of the vector u minus v. Can we count? What does it look like? What does it look like the components for that are? See, so here's minus v. So it looks like the x component is what, minus 2? And the y component, what? Positive. So it looks like u minus v should be, what did I just say there? What? Minus 2 and what? Positive 3? Is that what you get when you take the, is that what you get when you take the difference of the components? You get minus 2 and 3? See, here's the vector u, here's the vector v. So 2 minus 4 is minus 2, right? And 5 minus 2 is 3. Yeah, sure. Okay, so that matches up. Exactly just like you would expect, right? So the geometry makes it look like it's complicated, but it's not, right? When you're subtracting vectors, again, arithmetically, it's very simple. Just take the difference in the components, right? Okay, so let's try a little example here, and I'm going to have y'all do these for me very quickly. So here we have two vectors. V is minus 2 and 5. That's in component form. And W is 3 and 4, right, in component form. It says find each vector. So I've got some new vectors created here from V and W. And then it says sketch the graphs, but you really don't have to sketch the graphs, okay? So sketching the graphs is not really necessary there. So there are my two vectors, V and W. Write those down on your paper, okay? Because here's what I want you to compute for me. Let's see if I can get it all on here. Well, I cannot. All right, so there's 3 of them, though. Calculate these for me. Did y'all write down those two vectors? Okay. What were they? V was what? Negative 2 and 5. And W was what? W was 3 and 4. Okay, so calculate these for me. Minus 1/2 V, V plus W, W minus V. You don't have to draw a picture of them. Don't have to draw a picture of them. Just calculate them from these original vectors, V and W. Say your answer. Okay. Now quickly. Your homework. So. So that's all very easy, right? Kind of straightforward, okay, right? So when you practice, did y'all finish those? What's minus 1/2 v then? Yeah, so minus 1/2 times, so minus 2 is what, plus 1? And then minus 1/2 times 5 is minus 5/2. So did y'all get that? And then v plus w, that should be pretty straightforward, right? Just adding the components, right? So minus 2 plus 3 is 1. And then 5 and 4 is 9, right? So that's easy. And then maybe just a tiny bit harder, right, is doing the subtraction just because it involves subtraction, right? Let's make sure we do it in the right order. So w minus v is 3 minus a minus 2, right? So we have to be careful about the signs. And then what, 4 minus 5? And so that looks like that's going to be positive 5 and negative 1. Yeah. So easy, right? Oops, forgot the 1. What about 2w? That can't be hard, right? We're just going to be doubling the components, right, of w. So there's the components of w, right? So it looks like if we double those, we just get what, 6 and 8? And then there's just slightly more complicated, but not much, because we already have 2w, right? That's 6 and 8. And so we're going to add on that to the original v. What was that? Minus 2 and 5? And so that looks like what, 4 and 13? Okay. So see, scalar multiplication and vector addition and subtraction, those are really the easy operations for vectors. So we are going to expand our knowledge of vector operations to some operations that are a little bit trickier. Finally, one last definition in these notes, and then we'll be ready to switch notes. I don't think in the notes I defined unit vector, but unit vector is a vector that has magnitude 1, exactly 1. So a vector that has magnitude 1 is called a unit vector. And it's often useful to find the unit vector that has the same direction as a given vector. So you may have a vector that's not a unit vector, and often we want to sort of take that vector and kind of turn it into a unit vector. We can't really turn it into a unit vector, but when we say turn it into a unit vector, what we want to do is find a vector that has the same direction. It's going in the same direction as the given vector, but it does have length 1, right? So it's kind of shortening a vector to length 1 because it's very convenient for us for reasons that you'll see later to have vectors of length 1, okay? That's often useful to us. And so that's very easy to do. The way you can do that, the way you can find that unit vector is just take the original vector and divide it by its own magnitude, okay? That's a scalar operation because remember, magnitude is a number, right? Magnitude is not a vector. Magnitude is a length, right? Which is a single number. So if you take a vector and divide it by its magnitude, then you'll get a unit vector, but this unit vector will go in the same direction as the original vector. So just take each of the components of the original vector, divide them by the magnitude, you'll get a unit vector, but that points in the same direction as the original vector. Let's do that for three of these vectors that we just discovered, B, C, and E. I think I can get them all on the screen if I try. Yeah, okay. So see if you can find the unit vector that has the same direction as these each of these vectors, B, C, and E. Okay, so this is really just an arithmetic problem because all you have to do is find the magnitude. So you got to calculate the magnitude. Don't worry about simplifying it unless it's a very obvious square root, right? Unless it's a perfect square. And then you just divide each of the components by that, and that gives you the corresponding unit vector, right? Okay, so try that. That's just going to be a little bit of arithmetic. I don't want decimal approximation. So, definition. So take each component and divide by the total magnitude. That's the new vector. So it's going to look messy, probably, but its advantage is that it has new vector. It's 90. So it has exactly. Calculate the, yeah. So for instance, I should have done one example. Okay. So, so we want to find the unit vector, right, that corresponds to this vector, which is not a unit vector. This does not have magnitude 1, right? So calculate its magnitude. So calculate its original magnitude, right, which is just the a square root of the sums of the squares of the components, right? So you end up with, what is this, square root of 82? And you can just leave that as square root of 82. That doesn't really simplify anyway, okay? And then you just divide your components by that. So here's the vector that you get. Remember, I told you it's going to be messy. So it's 1 divided by the square root of 82 and 9 divided by the square root of 82. That vector has the same direction as this one, but this one does have magnitude 1. Okay, that one does have magnitude. So that's what you do. Okay, so do that one for B, and then also for C, and then for E. That's it. Yeah. That's it. It has exactly. See. Yes. Yes, that's it. Sure. Yeah, it seems to be complicated. let's actually that one that I just did. Let's check that one. Business. I really that's y'all are getting into. So what does this unit vector for C look like? What 5 over what is it? Square root of 26? And then minus 1 over square root of 26? Because this original vector had magnitude square root of 26, right? So just divide those into each of the components, and there's your corresponding unit vector. Let's make sure that this really is a unit vector. So let's make sure that it really does have magnitude 1. Not this one, but this one, right? So how do you calculate its magnitude, of course? How do you calculate its magnitude, of course? Well, you have to do what? Yeah. So you have to square the components, right? So we will get, let's see, 25 over 26, right? For this square, plus 1 over 26 for this square, right? And that looks like the square root of 26 over 26. And indeed, that's 1, right? So, so you see that has magnitude 1. What about for this last one? What did that work out to be? What, 4 over, what was it, 185 here? Square root of 185, and then 13 over square root of 185, right? Okay. All right, so there's our first set of notes, our easy here introduction to two-dimensional vectors. But now we're going to make it a little bit more fun, okay? Because what we haven't really done with the two-dimensional vectors yet is we haven't seen any applications of them. So what are these things good for? And then also we left open the question last time of vector direction. Remember, I said vectors incorporate two important quantities: magnitude, right? So we know how to compute magnitudes, but vectors have directions, and we didn't really have a good way so far of discussing the direction of a vector, all right, or trying to measure the direction of a vector. We can sort of see it geometrically, right? Okay, so we understand it geometrically, but if we were trying to get it out of the geometry and write down a sort of a numerical measure for the direction of a vector, not able to do that yet. Okay, so we have to take up that problem again. This is what's coming up in the second set of notes, right? That we're going to start here in just a second. Oh, great. So our timing is perfect. So let's take a little bit of a break here. All right. And I'll pause the tape, and we'll come back at 11:30, and we're going to talk about those two things, right? What is vector direction, and how do we apply vectors? We're also going to learn another way for expressing vectors, writing vectors down, but it's very similar to component form. Let me pause. Let me resume the recording. Okay, now we're gonna continue to express vectors in component form, but I'm going to slightly change the representation in component form in the following way. These two vectors are going to play a special role for us in expressing vectors. So this vector I is the vector that has length 1. This vector has length 1, but is horizontal. Okay, it points 1 unit to the right. All right. And this vector J is kind of its a counterpoint, but in the vertical direction. So this vector J has also magnitude 1, length 1, but it points straight up in the vertical direction. Okay. Let me show you a picture of these two vectors I and J, and we'll almost always reserve these letters I and J to represent these two unit vectors, these very simple unit vectors. There's a picture of I. Okay, so again, it has length 1, but points horizontally to the right. And here's the vector J that also has length 1, but points vertically. All right. These are called the standard unit vectors. I think that's the word that yeah. Okay. And now, the way we're going to use I and J is once we've got them defined, we can express other vectors that are in component form. We can express other vectors in component form as a combination of these two vectors. Let me show you how we do that. It's very simple. All right, so suppose we have this vector u, right? This is in component form, okay? And so I can rewrite that in terms of the vectors I and J in the following way, okay? So there's the vector u, right? Just these two simple components, 3 and 2. But notice I can take u and write it as a sum, the sum of these two vectors. Okay, so here's this vector would go 3 units horizontally to the right, and this vector would go 2 units vertically up, right? But of course, when you add these two vectors together, that gives you the vector u, correct? Now, you can write this vector and this vector as scalar multiples. So instead of writing 3, 0 here, I can write this as 3 times 1, 0. And then this vector, instead of writing 0, 2, I can write that as 2 times 0, 1, correct? Because of the way scalar multiplication works. But 1, 0, that's the unit vector, that's the standard unit vector I, and 0, 1, this is the standard unit vector J. So in other words, you've taken the vector u and you've written it as a combination of these two vectors I and J. And in the future, that's how we're going to write vectors in component form. Instead of using the brackets here, we will instead write them as combinations of I and J. That's not saving us any space, okay, right? But that turns out to be a convenient way of expressing vectors in component form, is in terms of as combinations of these two unit vectors I and J. Here's kind of a picture of what I just said there, right? Okay, so if that's the original vector u, right, we can write it as a combination of a multiple of the vector I and a multiple of the vector J. Let's do that because it's very easy. It's almost trivial, right? Writing a vector in this is called standard form, by the way, when you express a vector in terms of as a combination of the vectors I and J. That's called standard form. Component form is slightly different, but very similar. Let's try this quickly, but it's very easy to do. So let's see. Suppose we have a vector u, and its initial point is 2 and minus 5, and its terminal point is minus 1 and 3. Okay. And then suppose we have another vector, and this vector is 2i minus j. So this vector is written in standard form. That vector is written in standard form. Let's take those and use those to create some other vectors. First, though, let's just take this vector u that has this initial point and this terminal point, and let's write it in standard form. Okay, so what would u look like in standard form? So standard form means a combination of the vectors I and j. Well, To get that, first take the vector u and put it in component form. See, this is not written in component form because I gave you the initial point and the terminal point, right? So first, let's write it in component form. And how do you write it in component form? Remember, you just take the difference in the coordinates, right, between the initial point and the terminal point. So the terminal point is -1 is its x-coordinate. The initial x-coordinate is 2. So you get -1, -2 here, right, for the first component. And for the second component, take the difference in the y-coordinates there. So you get what? 3 minus a -5. See, what does that end up being? -3 and 2. Is that right? Did I do that right? -1 -2 is -3. -3 minus a -5 is, oh, that's 3 plus 5 is 8. So I didn't do it right. So you get -3 and 8 there. That's in component form. Now, what does that look like in standard form as a combination of the vectors I and j? So easy there. It's just going to be -3i plus 8j. So it's virtually the same, right, as component form. And now let's compute this vector w, which is supposed to be twice u minus 3 times v. Well, now this is kind of, once you've got these vectors written in standard form, this sort of becomes an algebra problem. So we would have 2 times u, which is -3i plus 8j, right? And then -3 times v. Let's see, what was v again? I forgot. 2i minus j. So 2i minus j. So let's see, what's all this calculation? See, these calculations look now like algebraic calculations, right? So you have -6i plus 16j minus 6i, what, plus 3j? And see, now you can add the I components together and the j components together, sort of like terms in algebra. So -6i minus 6i is -12i, and then 16j plus 3j is 19j. So I think the reason people find, or one of the reasons people find standard form convenient, is now when you're doing operations, you know, with vectors, it kind of is like, you know, doing operations in algebra, right? Simplifying expressions in algebra. Because you can sort of think of the I and J as being variables, but they're really not. Okay, those are actual vectors, remember? Okay, so these are not variables at all. In fact, they're actual things. Okay, these are actual vector constants. Now, another reason that a standard form is useful is now it gives us a better understanding of direction. Yes. Did I make an arithmetic mistake? Which negative sign? This one? Yeah, that no, not any longer, because the parentheses are gone. See, when I multiplied the -3 through here and the parentheses are gone, then this minus sign just applies to this term. -3 times 2i is -6i, right? And then -3, I did distribute the minus sign though. -3 times -j is plus 3j. So in effect, I did take into account the minus sign, but it made that a positive 3j. Yeah. Once the parentheses are gone, this minus sign just applies to this term. Yeah. Here, the minus sign does apply to both terms, though. You're right, but we took that into account. Okay. All right, now finally, let's talk about direction. All right, so you're gonna have to pay attention here because this is gonna involve some trigonometry. All right, so you're gonna have to remember a little bit from your trig experiences. All right, so I don't know how long ago that's been. All right, so we mentioned that slope is a slope of a line segment is not a good way of measuring direction of a vector, because unfortunately slope is directionless. All right, but we do want a way of measuring the direction of a vector, and so we are going to have to rely a little bit on trigonometry. Okay, so we're going to express the direction of a vector as being its when the vector is in standard position, when that means its initial point is at 0, 0. The angle that the vector forms with the x-axis, that is going to be the direction of vector. Okay, so the angle it forms with the x-axis when it's in standard position, that's the direction of a vector. Here's the picture of that. Okay, so here's a vector u, right? Okay, and so that one's a little bit simple because the u ends up being in the first quadrant, right? So it'd be more interesting if it's in one of the other quadrants, but so be it. All right, so there's a vector u, and again, this angle that u forms with the x-axis, that's what we're going to describe as being direction of vector. Okay, now if the vector is a unit vector, then this direction shows up very nicely in the representation of the vector. Right? Let me show you why. Okay, so here's a vector u, and imagine that u is a unit vector, so it has length 1. Okay, so what I'm discussing here applies to unit vectors only. Okay, all right, so imagine that you have this vector u and it has length 1. So that means the length of this arrow, right, is 1. Okay, all right, now I've got you positioned in the first quadrant because that makes it easier to draw this picture. But the same logic applies is if u is pointing into any of the other quadrants. The same logic will apply. It's just not as easy to visualize. Okay. All right. So there's that theta. That's the direction of u, correct? Right, because that's the angle that the vector u forms with the x-axis. Now I'm going to draw a right triangle here. All right. So let's drop a line segment, a vertical line down from the end of the vector u down to the x-axis. Okay. Of course, when you do that, you get a right triangle, right? But notice the hypotenuse of this right triangle is 1. So the hypotenuse of this right triangle is 1. So that really simplifies this picture here, right? So look at what the opposite side of theta is. Here's the opposite side of theta, right? In this right triangle, that's opposite. That side is opposite. Of course, this is the hypotenuse, right? But this side is opposite of theta. Now, how would you calculate then the sine of theta? Well, you always calculate sine of theta in the same way, right? What do? You take the opposite side, right, and divide it by the hypotenuse, correct? In right triangle trigonometry, that's how you compute sine of theta, right? But notice that in this picture, the hypotenuse is 1, correct? So this just simplifies to opposite over 1, which is just the same as the opposite, correct? So notice the opposite side here is the sine of theta, right? Sine of theta is the length of this side. Okay, that's just because this is a unit vector. Now, what about for the adjacent side here? Same thing. That's going to turn out to be exactly the cosine of theta. So the length of this adjacent side is cosine of theta. Oh, well, look then. What is then the vector u? Notice then that this horizontal length is what? Cosine of theta, correct? This vertical length is what? It's just sine of theta, right? Because this length is cosine of theta, this length is sine of theta. Oh, so there's how you can write the component form of the vector. It's just cosine of theta. That's the direction of the vector, right? And then it's the sine of theta. Theta, remember, is the direction of the vector. Keep in mind, though, this only applies to a unit vector. This had to be a unit vector, right? So for a unit vector, here's what it looks like in component form. It's the cosine of its direction and the sine of its direction. Now, if you want to take that and put it in standard form in terms of I and j, well, you get cosine of theta times I plus sine of theta times j, right? Ooh, that's really kind of an important equation there. So for a unit vector, here's how you can always write down its representation. It's the cosine of its direction times I plus the sine of its direction times j. Now you might say, well, that's great, but that direction is kind of tricky to determine, right? Well, that's true. Okay. The direction is going to be hard to measure, right? For unit vectors, if you're just looking at the picture. But nevertheless, this equation still is true. Now, what about for vectors that aren't unit vectors? So what about vectors that aren't unit vectors? So suppose we have a vector v that's not a unit vector. But look, you can write v always as its magnitude times a unit vector. That's right, correct? Look, so if you have a vector v, looks like this, right? It has a couple of components, correct? Those can be any two. Those can be any two numbers there. Remember, I said if you wanted to write that in, if you wanted to write the unit vector that has the same direction as v, what do? We did that just a moment ago. So how do you find the unit vector? That's the vector with length 1 that has the same direction as v. What do? You divide the components by what? By the magnitude, right? So if you wanted to find the unit vector that has the same direction as v, take v and divide it by what? Its magnitude, correct? That new vector will be a unit vector, right? It will have length 1. What do its components look like? We just did that a moment ago, right? So you have v1 divided by the magnitude of v, right? And v2 divided by the magnitude of v. But now, what happens when you take u, this new vector, what happens when you take that and multiply it by the magnitude of v? What do you end up getting? So if you take this new vector u and multiply it by the magnitude of v, what happens up here? So if you multiplied everything by the magnitude of v, what happens to these magnitudes of v here? They cancel, and what do you end up with again? Yeah, you just end up with the vector v back again, right? Okay. That's what this equation is essentially saying. It says for any vector, you can write it as its magnitude, its own magnitude times a unit vector. This is the unit vector that you would multiply by, okay? So for any vector v, you can express it as its magnitude times a unit vector. But now, what did we just learn about unit vectors? How can we write them down? In what way? In standard form, right? And what does the standard form look like for unit vectors? It's always what? Cosine of what? The direction times I plus sine of the direction times j. So for any vector, you can write it as its magnitude. See, there's its magnitude times what? Cosine of its direction times I plus sine of its direction times j. That gives us this is really an important equation here, right? Okay, so for any vector, you can always write it as its magnitude times the cosine of its direction times I plus its magnitude times the sine of its direction times j. That I boxed this off because I wanted you to remember that. Okay, this equation is important. So for any vector, magnitude times the cosine of the direction times I plus magnitude times the sine of the direction times j. And keep in mind, theta here is direction. What's the direction? How do you describe that? It's the angle formed what? The angle formed between and the vector. Yeah, okay. So the direction is the angle formed between the x-axis and the vector. Keep in mind that you're measuring that angle counterclockwise, right? Because that's how we measure angles, right? In trig, measure them counterclockwise. Unfortunately, in some of our applications, angles are going to be measured in the other direction, and that gets really confusing. But not for mathematicians. We always measure angles counterclockwise. Okay. Well, all right, let's practice with this because this equation just is an equation, right? Until we actually apply it. So let's look at an application here. So suppose I'm thinking of a vector and it has magnitude 3. Okay, all right, and its direction is pi over 3. That angle pi over 3. And we can draw a picture of that really pretty easily, right? So, you know, a really ugly sketch of it. So here's the vector v. There's the vector v. That's supposed to be a y, not a v. So here's the vector v, and its angle is supposed to be what? Pi over 3. And its length was supposed to be how much here? What did it say? Its magnitude? 3, right? So this length is 3. So I'd like to know what this point is, because if I knew what this point was, right, I could write down the vector in standard form, which is what I want to do. Okay, so we want to write the vector out in standard form. So, so if this angle is pi over 3, and this vector is supposed to have length 3, then what's this? What's that point though? So I can write it down in standard form. That's so easy now, though. Okay, you don't have to do any calculations at all because this equation tells you already. See, we've done the hard work already. This angle in standard form is its magnitude. What's the magnitude here? 3 times the cosine of its direction, which is what? Pi over 3 times I plus magnitude times the sine of the direction times j. Wow, see how easy that was? So I don't have to do any trig here at all from this picture because I've already done that work already. It's already incorporated into this equation. So, but we do have to remember what cosine of pi over 3 is and what sine of pi over 3 is. Wow, do I remember that now? Cosine of pi over 3 is, do I remember that? It's 1/2, yeah, okay, which is 0.5, but did you get that 0.5 from your calculator? Okay, all right, that one you want to remember because that's a special angle. So cosine of pi over 3, you want to remember that's 1/2, right? And what's the sine of pi over 3? So you don't want to get that from your calculator because that's going to look terrible. What? Square root of 3 over 2? Yeah, times j, right? So we end up here with 3/2 I plus what? 3 square root of 3 over 2j. Oh, there it is. So easy. Are y'all gonna need some help with special angles? Remembering those? I'll bring y'all a sheet that will help you remember that a little bit. Okay. Sines and cosines for special angles. We won't need those as nearly as frequently as you need them in calculus 2, but they may come up from time to time. All right, now let's make the problem harder though. So I should have drawn a picture here, but I didn't. So well, we can sketch one. So here we have a vector, but this is already written in standard form. So it's 160i minus 400j. So how is that vector pointing? Into what quadrant? Yeah, I've gotten almost every answer there. I had first, second, and fourth. No one said third. Okay. Is it fourth? Yeah, positive x, negative y, right? So it's coming over 160 this way and down 400 this way, right? So somewhere way down here, right? Something like this is what the vector v looks like, right? So it's got a really big direction, correct? But you can also express the direction like this too, okay? But remember that this angle is negative, okay? This angle in the counterclockwise direction is positive. But what we want to find out is what is exactly that magnitude and what is this direction? Okay, so what is that angle, right? All right, so but let's remember, so V is going to be in component form, right? It's going to be its magnitude, right, times the cosine of its direction times I, right, plus its magnitude times the sine of its direction times j. And we're trying to figure out the two unknowns in this equation, right? Okay, which are the magnitude and the direction. I and j are not unknowns, right? Those are vectors. So we know the values of I and j. But we don't know in here the magnitude of v yet, and we don't know this direction. But so we got to start filling in the blanks here. But what can we calculate easily? Magnitude, right? Okay. So let's try that. And that does require a little bit of arithmetic, so y'all gonna have to help me with this. Let's go up here and try it. So the magnitude of v is going to be the square root of, see, we got big numbers here, 160 squared plus the negative 400 squared, right? The square root of that. So what are those numbers? What's 160 squared? 200, is it 256,000 or something? Is that right? Or is it 25,600? I'm not sure. You'll calculate that for me? Okay. Oh, it is 25,600. Oh, okay, so I did overshoot it there. So 25,600 plus 160,000. That makes sense. So that ends up to be the square root of 185,600. And who knows what that is except for the calculator, correct? Okay. Let's leave it in exact form for a moment, though. All right. And then later on, we'll probably need a decimal approximation when we're trying to figure out what theta is, correct, right? Okay. But we'll leave it in this form for a moment. So let's fill it in here. So we get square root of 185,600 times the cosine of theta times I, and then plus that same big square root, 185,600, right, times the sine of theta times j, correct? Now, however, I want to point out something. Here is v written in standard form, but here is also v written in standard form. So notice we know what the coefficient of the I is, and we know what the coefficient of the j is. This number is supposed to be what? 160, right? And this number is supposed to be minus 400. Is that right? So what you know is, oh, something useful. Square root of 185,600 times the cosine of theta, that has to turn out to be 160. So guess what the cosine of theta is? Well, it's 160 divided by this, right? And same thing for sine of theta, right? 185,600 times sine of theta has to come out to be minus 400. So that means the sine of theta is minus 400 over square root of 185,600. Now you're in business, right? Because how can you now figure out what theta is from this equation? What would you apply to both sides here? Yeah, that's right. You would apply inverse cosine, right? So take the inverse cosine. See if I can squeeze that in here. So the inverse cosine of 160 over square root of 185,600. That's one way of doing it. Or you could use this equation as well, right? So you would have that theta is equal to the inverse sine of minus 400 over square root of 185,600. Let's try this one. I like this one better, I think, than this one, than doing this one. And that has to do with the way inverse sines and inverse cosines work, right? Okay. When you take the inverse cosine of a number, you get an angle, but the angle has a limited range. What's the angle turn out to be? Between what and what? Do you recall this? Not between 0 and 90. Yeah, for inverse cosine, this is easy to forget. For inverse cosine, you always get an angle between 0 and pi, between 0 and 180 degrees. Okay, so when you solve this equation, you would get an angle from 0 to 180 degrees. You would have to adjust your answer then that you get, okay? You would have to adjust your answer to take into account that the angle that you're really looking for is in the fourth quadrant, right? Okay, so you can make that adjustment. You can make that adjustment, but you'd have to think about it a little bit, okay? When you take inverse sine of a number, you remember what the range of the inverse sine is going to be? You always get an angle between, not between 0 and pi. You get an angle between pi over 2 and minus pi over 2. Oh, I like that. Maybe I like that better. Okay. Because here I would get possibly this angle. Okay. As my direction. Let's try that and see what you let's try that and see what you get. So can y'all do that with your calculator? So take minus 400 divided by the square root of 185,600 and then compute inverse sine for that. Maybe we can do it here on this calculator. See what happens. Whoops. So 185,600. Let's take the square root of that. Did that calculate? So that's 430. Now let's invert that. So let's take 1 over x and multiply that by 400. So I get this. Let's change the sign because it was supposed to be negative, right? And now let's compute the inverse sine of that, right? And I get what looks possible there, minus 60.52 degrees, right? So it looks like we could use as our direction here, minus 68.2. Okay. If you wanted to write that, of course, if you wanted a positive angle, so if you want to write your direction as a positive angle, just add 360 degrees to that, right? So take 360 and subtract off 68.2 degrees. And you could also write your direction that way. What would that turn out to be? 291.8 degrees. Okay. So you can also try that direction. Oh, neat. So there's theta. Theta is, we can either write minus 68.2 degrees or we can write 291.8 degrees. If you, what happens if you calculate, let's try calculating it this way and see if we can figure it out correctly. So let me pull up the calculator again and see if we can do it that way. All right, so let's see. We have here again the 185,000. What was it? 600? And then I want to take the square root of that. Okay. And then let's invert that and multiply it by, what's it supposed to be? 160 for cosine. So 160 gives us this number. Is that right? Oh, yeah, that's probably right. Okay. And now let's take the inverse cosine of that, and we get 68.2. Okay. But remember, okay, of course, that angle is in the first quadrant, right? So you want an angle in the, but you want your angle in the, you want your angle in the fourth quadrant, okay, not in the first quadrant. So you have to think about, oh, what angle in the fourth quadrant is going to have reference angle 68.2 degrees, right? Okay, well, of course, it's either got to be minus 68.2 degrees or it's got to be this big angle, right, that loops around. That's the 291.8 degrees. So you could figure it out you could also figure out from this equation the correct direction, but you have to be careful about it, okay? Because if you just wrote down 68.2, you would have a direction in the first quadrant, which is not what we wanted, right? Okay. All right. Well, let's stop there, and because we're out of time. But now I know what we'll resume with next time. So this is going to be our recall practice for next time. We're going to try to do this problem again. We have to break it up into steps, right? So there I have a nice simple vector, minus 7i plus 5j. Where's that? Quadrant 2? Yeah. So that's in quadrant 2. I want to figure out what is its magnitude. That's easy, but what is its direction? So what is the angle for this vector somewhere there in quadrant 2? So it's going to be some angle bigger than 90 degrees, right? Okay. Let's see if we can figure that one out exactly next time. Well, we didn't quite get to our applications. Darn it, we didn't quite get to our applications from physics, but we'll finish that quickly next time. You do have maybe one problem in your homework that's an application problem. So you do need to see these application problems before you can finish that homework. Okay, so we're done for today, and we got our first week under our belt. Oh, we didn't see any calculus. Darn it. But it's certainly coming up. Oh, there's oh God, very next example. There's a calculus problem. Okay, so we're close to it. All right. Okay, but not quite there yet. So we'll hit that pretty quickly on Monday. Okay. Have a great weekend, and we will have another week, and then we have a holiday, right? So we got something to look forward to there if we can get through next week. So I'll see you guys on Monday. Just leave your card. Oh, I forgot to pass out the roll sheet, but that's okay. Oh, I don't need that yet. I think we have everyone accounted for except for one person. Anyway, so we'll start taking roll on Monday. And I'll see you all then. All right. Bye. Let's see if I can make this recording happen.